The Katechon Hypothesis. By Anatoly Karlin, that which withholds Eschaton, the Katechon Hypothesis for resolving the Fermi paradox. Filtering the Great Filter. Robin Hansen's answer to the Fermi paradox, where is everyone, is that the apparent rarity of advanced alien civilizations is due to some bottleneck event that all intelligent life has to go through. One may view this concept as an extension of the Drake equation, under the additional assumption that some of its values are so low that the average galaxy isn't likely to host much more than one civilization that emits detectable signals into space at any particular point in time. It is possible that the Great Filter lies in our past, meaning that we are safe, and a ball of hedonium may soon envelop our planet and suffuse our future light cone. In a recent paper, a team of futurists recalculated the Drake equation. Instead of using point estimates, which typically yield an infinitesimal probability of our galaxy containing no alien civilizations, they calculated the distribution of expert probability estimates, ran a Monte Carlo simulation, and deduced that there is a 1 in 3 chance that we are alone in our galaxy, effectively dissolving the Fermi paradox. We should hope that they are correct, since the alternative possibility, that the Great Filter lies in our future, very likely dooms us to imminent extinction. Shadows of the past. If the Great Filter lies in our past, then it would imply that at least one of the former is very rare or improbable. The evolution of life. Certain evolutionary milestones. The evolution of intelligence. Advanced technological civilization. The evolution of life. Straddling the warm Goldilocks zone between the sun and the cold emptiness of outer space, perhaps Earth was uniquely optimal for the emergence of life. This rare Earth hypothesis has been challenged in recent years by the discovery of vast numbers of Earth-like planets. However, perhaps a weak version of REH might still hold, that Earth is optimal for the fast emergence of complex, intelligent life. For instance, at least 2 critical evolutionary leaps, the appearance of eukaryotes and of large metazoans, may have depended on large, creative, destructive oxygenation events. If the Earth's oxygen absorption capacity had been higher, complex life might not have had time to emerge by the time the sun fried our planet in another billion years. Evolutionary milestones. Life appeared, in geological terms, almost immediately after the formation of Earth. So abiogenesis is unlikely to have been the principal barrier. Following the evolution of the first self-replicating molecules, there was 1.8 billion years of near biological stasis. Perhaps the likeliest candidate for the Great Filter was the transition from prokaryotes to eukaryotes, which were a prerequisite for the appearance of complex, multicellular organisms and sexual reproduction, both of which may have also been improbable. Conversely, transitions that evolved independently on many separate occasions, limbs, sight, photosynthesis, may be safely ruled out. The evolution of intelligence. Nervous systems with distinct neural signaling molecules, the building blocks of big brains and intelligence, evolved independently across both ctenophores and cnidarians bilaterians 500 million years ago. Moreover, according to the Red Queen hypothesis, organisms don't exist in a vacuum, but need to compete against other organisms within a mutable environment. Since you can't stand still indefinitely, this should drive the evolution of more complex life forms. This theory is backed by evolutionary history. Since the Cambrian explosion 550 million years ago, the maximum encephalization rate has been constantly doubling every 50 million years. More broadly, there has been exponential growth in minimum genome size since the dawn of life. As Pierre Teilhard de Chardin and Vladimir Vernadsky had intuited in the 1920s, evolution is creative, with an overarching teleological drive towards greater complexity and intelligence. Nor is there good reason to believe that there is anything particularly unique or improbable about human intelligence. The world after the dinosaurs has seen convergent evolution of greater intelligence across the entire swathe of the world's habitats and animal taxa. Dolphins, whales, and octopuses in the oceans, corvids and gray African parrots in the skies, and the great apes, elephants, and some monkey species on land. If humans were to disappear off the face of the planet today, there will be plenty of candidate species to rekindle civilization. For our own part, hominins only split off from primates 15 million years ago, and our brains have been exploding in size and capability ever since. Even the theory that there was a discrete, great leap forward in human behavioral modernity 50,000 years ago has been sidelined in favor of explanations stressing continuous and accelerating change-advanced technological civilization. Technological growth has been increasing at an exponential rate with remarkable consistency for mankind's entire history. Agriculture began 10,000 years ago. The Industrial Revolution took off around 1780. In the past couple of decades, the new science of cliodynamics has provided a strong theoretical basis for this pattern. The basic idea is that as population rises, you get more potential inventors who create more technology and increase the carrying capacity of the land, resulting in higher populations, more potential inventors, etc. Although this basic mechanism is punctuated by Malthusian cycles, a euphemism for population collapses in the wake of disasters such as droughts, famines, plagues, civil wars, and nomad invasions, the exponential trend was remarkably stable in the long run. Other positive feedback loops include literacy and technologies to create more technologies, such as paper, reading glasses, the printing press, and computers. Human accomplishment, as proxied by the per capita incidence of great scientists and artists, also rises exponentially over the past 2,500 years, peaking in the late 19th century. The history of science and technology is also replete with examples of convergent evolution. Fire was invented, forgotten, and reinvented by countless numbers of disparate human bands. Both agriculture and literacy were independently discovered across multiple locations. The ancient Greeks almost got to the steam engine, and there were proto-industrial revolutions in the Roman Empire and Song China before the real deal got going in late 19th century Britain. At that point, the scientific revolution had been ongoing for more than 2 centuries, and more than half the denizens of the European core were literate. At that point, even if Britain had been swallowed up by the sea, an industrial revolution in that region of the world had long since become inevitable. Gloomy presentiments. Future. Great filters are mostly coterminous with the concept of existential risks and determine the value of the final term in the Drake equation, which refers to the length of time over which advanced civilizations release detectable signals. In a seminal paper, Nick Bostrom defined X risks thus: 1, where an adverse outcome would either annihilate Earth-originating intelligent life or permanently and drastically curtail its potential. He also pointed out that a very strong indication that the great filter lies in our future would be the discovery of evidence of past life, especially complex life, on Mars or elsewhere in the solar system. At a single stroke, this would rule out the earliest and some of the strongest candidates for the great filter at a single stroke, and would constitute by far the worst news ever printed on a newspaper cover. Major candidates for future great filters can be divided into 3 major bins: geoplanetary, for example asteroid impacts; gamma-ray bursts, GRBs; geomagnetic reversals; supervolcano eruptions; megatsunamis. Technogenic, for example nuclear warfare; anthropogenic climate change; pollution; resource depletion; dysgenic decline; bioweapons; nanotech; malevolent AGI. Theoretical, for example, super-predator civilizations. Our simulation shuts down. Geoplanetary X risks. These are characterized by being either eminently survivable, at least on a civilizational scale, or highly unlikely even on Terran timescales. One study found that there's a 1% chance that our galaxy will produce a GRB any time in the future, let alone one pointed at the Earth in the near future. If our hunter-gatherer ancestors survived the Toba eruption 72,000 years ago, then modern civilization will surely survive another Yellowstone eruption. An asteroid impact on the level of the KT extinction event, which did in the dinosaurs, is only expected to happen once every 100 million years. No dangerously large asteroids have been observed on a collision course with Earth, and even if they were, Well, if early mammals survived KT, then so will humans in deep bunkers and nuclear submarines. All of these scenarios will be extremely disruptive, causing dozens, if not thousands, of megadeaths. But in almost all these scenarios, some humans will survive, and they will be able to rebuild industrial civilization. It can't be completely excluded that a really large asteroid, 100 kilometers in diameter, a GRB burst, or something more exotic hits us. However, it would be extremely strange, not to mention extremely suspicious. If a geoplanetary Götterdämmerung was to do us in just 200 years after the invention of radio, during a time when we might be at the cusp of a technological singularity, then again, we wouldn't have long to speculate about the cosmic injustice of this, which may well be the main point. Technogenic X-risks. This consists of classic 20th century concerns, nuclear war, dysgenics, and resource depletion, today's hot topic of man-made climate change, and futurist concerns such as GNR, genetics/nanotech/robotics, technologies and machine superintelligence. The megatonnage of the world's nuclear stockpiles are an order of magnitude lower today than during the height of the Cold War. Not to mention 6 orders of magnitude lower than the energy released during the Chicxulub impact that did in the dinosaurs. Even so, many serious assessments, even during the Cold War, projected that a solid majority of the American population would survive a full nuclear exchange with the USSR. Tens of millions would die, and the bulk of the capital stock in the warring nations would be destroyed. But as Herman Kahn might have said, this, as his parody in the movie Dr. Strangelove said, this would a regrettable but nevertheless distinguishable outcome compared to a true existential risk. In the long term, radioactivity will dissipate, the population will recover, and infrastructure will be rebuilt. In the past decade, climate activism has aroused the same intensity of passion as concerns over nuclear war in an earlier age. But we need to keep things in perspective. The IPCC does not project global warming much greater than 5.0 degrees Celsius by 2100, even under the most pessimistic emissions scenarios. There is also a case to be made that moderate global warming may be a net good in terms of crop yields due to greater precipitation and carbon fertilization. However, even the most extreme projections, such as the Clathret gun going off and zones of uninhabitability spreading across the mid-latitudes, are unlikely to translate into James Lovelock's apocalyptic visions of breeding pairs, desperately eking out a hardscrabble survival in the Arctic. The Arctic was a lush rainforest when global temperatures were at such elevated levels and will be able to support advanced civilization. More importantly, there just isn't enough sequestered carbon to lead to a runaway greenhouse effect that turns our planet into Venus, at least under current levels of solar radiation. A relocation of the locus of human civilization towards the far north is not an existential risk. Similar considerations apply to pollution and resource depletion, confusing degradation and difficult adjustments with existential risks. First, it is not clear that things are actually getting worse. Environmental standards have been soaring in the developed world. For example, the Thames is now cleaner than it was in the 16th century, and new technologies are constantly opening up access to previously inaccessible resources, for example, hydraulic fracking. Second, while future energy shocks may still impinge on living standards, there are no grounds to think they will cause long-term economic decline, let alone technological regression back to Stone Age conditions, as some of the most alarmist doomers have claimed. There are still centuries worth of coal and natural gas reserves left on the planet. Nuclear and solar power have only been exploited to a small fraction of their potential, and hydropower, which has some of the highest energy returns on energy invested, isn't going anywhere. Furthermore, we still have a lot of potential fat to cut. Low car ownership and the extinction of budget airlines do not preclude continued radio emissions or rocketry. For example, see the USSR. Much of the developed world has experienced dysgenic reproduction patterns, duller people having more surviving children than brighter people, for over a century. Although this was long masked by IQ gains from better schooling and nutrition, That process seems to be coming to an end. Meanwhile, the problems that need to be solved for scientific and technological progress to continue are getting harder, not easier. Since almost all scientific discoveries accrue to a small cognitive elite in the world's rich, high IQ nations, this suggests that technological progress may slow to a crawl during this century as the world's remaining smart fractions get depleted, assuming that there are no abrupt discontinuities in humanity's capacity for collective problem solving, such as genetic IQ augmentation or machine superintelligence. But will this idiocracy be permanent? I doubt it. Since fertility preferences are heritable and ultra-competitive in a post-Malthusian world, we can expect an eventual reversal of the demographic transition. This renewed expansion will last until the world hits the carrying capacity of the late industrial economy, ushering in the return of Malthusianism and reasserting the eugenic fertility patterns of the pre-industrial world. Consequently, dysgenic decline does not constitute an existential risk. However, it may have the effect of extending the period of time that future humanity will be subject to increased levels of other existential risks. The final major source of technogenic existential risks concerns new technologies, in particular genetics, nanotechnology, and robotics, GNR. In an ideal world, they promise us a utopian future of radically expanded lifespans and abundant material wealth, if not the secular equivalent of transcendence. But GNR technologies may also be the instruments of our demise. Since bioengineering doesn't require an extensive industrial infrastructure like a nuclear weapons complex, the means to inflict massive damage may be democratized, vastly increasing the probability of devastating pandemics unleashed through bio-error or bioterror. The engineer Eric Drexler has suggested that nano-engines of creation may go rogue and blanket the planet in a sea of gray goo. However, it is hard to imagine an artificial virus that couples a 100% infection and mortality rate, while subsequent research suggests that democidal nanomachine swarms will remain in the realm of science fiction. That said, there are many unforeseen pitfalls. Future technology is, almost by definition, unpredictable. So it is not impossible that even something that currently seems highly unlikely, for example, particle accelerator experiments, if not a complete black swan, is what will do us in. Many experts believe that artificial general intelligence, AGI, will appear by the middle of the 21st century. And artificial general intelligence, AGI, may be able to quickly bootstrap itself into a superintelligence defined by Nick Bostrom as any intellect that greatly exceeds the cognitive performance of humans in virtually all domains of interest. Especially if this is a hard takeoff, the superintelligence will also likely become a singleton, an entity with global hegemony. And woe to us if it decides to convert us all into paperclips. Consequently, the control problem in AI is widely considered to be the most acute existential risk in futurist circles. It also happens to be largely irrelevant to this thesis, as it is one of the few existential risks that do not also constitute a great filter. Getting turned into paperclips will be bad for us, but irrelevant so far as the Fermi paradox is concerned. Functionally, all that will happen is that superintelligent machines replace humans as the primary agents of the Terran noosphere. Even if Skynet ends up killing us all, why would it stay on this planet indefinitely? More precisely, why would each one of the dozens to millions of past Skynets in our galaxy have uniformly decided to stay on their home planet, instead of beaming their presence out into space or physically expanding their dominion at close to the speed of light? Either machine superintelligence inevitably tends to suicide or stasis, which seems intuitively unlikely, though impossible to rigorously disprove since we cannot know the mind of a superintelligence before inventing one. Or superintelligences have universally worked out that they shouldn't broadcast or expand into space from first principles. Assuming that we cannot dissolve the Fermi paradox to be sufficiently confident in our own solitude, and that geoplanetary and technogenic existential risks don't constitute credible great filters, what else could possibly explain the great silence all around us? Universe simulations. Anyone who believes exponential growth can go on forever in a finite world is either a madman or an economist. Kenneth Boulding. The concept of super-predator civilizations that winnow out any civilization that shows its head above the cosmic parapets to remove potential competitors for resources out of pure psychopathy is a popular sci-fi trope. Perhaps the reason everyone is silent is because killers stalk the star-strewn skies, hiding in the dark voids between worlds. I do not consider this to be a very plausible explanation, at least so far as the most commonly cited reasons are concerned. Since any such civilization will have many millions, if not billions of years of technological advantage, a post-human space empire is unlikely to see any civilization at humanity's 21st century technological level as any sort of significant threat. Nor do I think it likely that they hunger for any resource specific to our humble clump of rock. The universe is full of rocks. Maybe they do it just for the hell of it, like the Reapers of the Mass Effect universe. Still, I don't think that's too likely. First, at least within the human species, empathy has tended to increase with literacy and social complexity. So it's not too obvious that an evil xenocidal race stalking the heavens would constitute the endpoint of sociocultural evolution. That said, as I will explain later, evolutionary dynamics may favor the emergence of such civilizations. Second, and more importantly, why would they snuff out fledgling space-traveling civilizations from the shadows, leaving open the chance that some particularly paranoid ones slip by their net, instead of openly exerting dominance and saturating the galaxy with their presence? Calculating space. But what if the resource in question is something a bit more esoteric? In a classic paper from 2003, Nick Bostrom argued that at least one of the following propositions is very likely true: that post-human civilizations don't tend to run ancestor simulations, that we are living in a simulation, or that we will go extinct before reaching a post-human stage. Let us denote these basement simulators as the architect, the constructor of the Matrix world simulation in the eponymous film. As Bostrom points out, it seems implausible, if not impossible, that there is a near uniform tendency to avoid running ancestor simulations in the post-human era. There are unlikely to be serious hardware constraints on simulating human history up to the present day. Assuming the human brain can perform approximately 10 to the power of 16 operations per second, this translates to approximately 10 to the power of 26 operations per second to simulate today's population of 7.7 billion humans. It would also require approximately 10 to the power of 36 operations over the entirety of humanity's 100 billion lives to date. As we shall soon see, even the latter can be theoretically accomplished with a nano-based computer on Earth running exclusively off its solar irradiance within about 1 second. Sensory and tactical information is much less data-heavy and is trivial to simulate in comparison to neuronal processes. The same applies for the environment, which can be procedurally generated upon observation as in many video games. In Greg Egan's Permutation City, a sci-fi exploration of simulations, they are designed to be computationally sparse and highly immersive. This makes intuitive sense. There is no need to model the complex thermodynamics of the Earth's interior in their entirety. Molecular and lower details need only be rendered on observation. And faraway stars and galaxies shouldn't require much more than a juiced-up version of the Universe Sandbox video game sim. Bostrom doesn't consider the costs of simulating the history of the biosphere. I am not sure that this is justified, since our biological and neurological makeup is itself a result of billions of years of natural selection. Nor is it likely to be a trivial endeavor, even relative to simulating all of human history. Even today, there are about as many ant neurons on this planet as there are human neurons, which suggests that they place a broadly similar load on the system. Consequently, rendering the biosphere may still require 1 or 2 more orders of magnitude of computing power than just all humans. Moreover, The human population and total number of human neurons was more than 3 orders of magnitude lower than today before the rise of agriculture. That is irrelevant next to the animal world for tilde 99. 9,998% of the biosphere's history. Simulating the biosphere's evolution may have required as many as 10 to the power of 43 operations. I'm not sure whether 10 to the power of 36 or 10 to the power of 43 operations is the more important number so far as generating a credible and consistent Earth history is concerned. However, we may consider this general range to be a hard, minimal figure on the amount of boring computation the simulators are willing to commit to in search for a potentially interesting results. Even simulating a biosphere history is eminently doable for an advanced civilization. A planet-scale computer based on already known nanotechnological designs and powered by a single-layer matryoshka brain that cocoons the sun will generate 10 to the power of 42 flops. Assuming the architect's universe operates within the same set of physical laws, there is enough energy and enough mass to compute such an Earth history within 10 seconds. And his is assuming they don't use more exotic computing technologies, for example based on plasma or quantum effects. Even simulating 10 billion such Earth histories will only take approximately 3,000 years, a blink of an eye in cosmic terms. Incidentally, that also happens to be the number of Earth-sized planets orbiting in the habitable zones of sun-like stars in the Milky Way. So far, so good, assuming that we're more or less in the ballpark on orders of magnitude. But what if we're not? Simulating the human brain may require as much 10 to the power of 25 flops, depending on the required granularity, or even as many as 10 to the power of 27 flops if quantum effects are important. 62, 63. This is still quite doable for a nano-based matryoshka brain, though the simulation will approach the speed of our universe as soon as it has to simulate approximately 10,000 civilizations of 100 billion humans. However, doing even a single human history now requires 10 to the power of 47 operations, or 2 days of continuous matryoshka brain computing, while doing a whole Earth biosphere history requires 10 to the power of 54 operations, more than 30,000 years. This will still be feasible or even trivial in certain circumstances, even in our universe. Seth Lloyd calculates a theoretical upper bound of 5*10 to the power of 50 flops for a 1 kilogram computer. Converting the entirety of the Earth's mass into such a computer would yield 3*10 to the power of 75 flops. That said, should we find that one needs significantly more orders of magnitude than 10 to the power of 16 flops to simulate a human brain, we may start to slowly devalue the probability that we are living in a simulation. Conversely, if we are to find clues that simulating a biosphere is much easier than simulating a human noosphere, for instance, if the difficulty of simulating brains increases non-linearly with respect to their numbers of neurons, we may instead have to conclude that it is more likely that we live in a simulation.